In the last set of in-class activities, we looked at a lot of different techniques for finding new rings. We're going to extend one of those techniques, and it's going to give us something called the subring test. So first we're going to define what a subring is. We're going to figure out what is necessary to actually prove that in some subset of a ring is actually a subring. And then finally we're going to look at an example. So recall the example of a ring, the set of even numbers. I'm going to focus on three properties of the set of even numbers. First of all, as we've proven, it is a ring. It is also a subset of the integers, which is also a ring. And then finally, the even numbers and the integers use the exact same addition and multiplication. In other words, the addition and multiplication we use on the even numbers when we're thinking of them as elements of the ring E is the same multiplication and addition we would use on those same numbers if we were thinking of them as elements of Z. So this is going to be precisely what we mean by a subring in general. Except we're going to do it in a general ring. So we're going to assume that R is a ring. We're going to say that S is a subring of R if three things happen. First of all, S is a subset of R that contains elements that are also in R. S is itself a ring. And when we're looking at the addition and multiplication, the addition and multiplication we use in S is the same multiplication and addition we use in R. So I just want to note that not every subset can be a subring. There's lots of examples of non-subrings. So for instance, if our ring is the integers, if we look at the set just containing 1, 4, and 5, that is very much not a subring. It is not closed under addition. It doesn't have an additive identity. Doesn't have additive inverses. Lots of things are missing from S to make it a ring. So it's not a subring. So it's a subset of R, but not a ring. So if we look at an example of S being the set of odd numbers, this has a few new properties, right? It is a subset of R. It is closed under multiplication, but it is not closed under addition. It has no additive identity, not a ring. So what we would like to have is a way of determining when the subset of a ring is a subring. And we would not want to go through all the ring axioms to prove it. There are a ton of ring axioms. It would be nice if we could somehow make it a little bit more efficient. So let's suppose we have R a ring. Suppose we have a subset S of R. And let's think about all the things that we would in principle have to prove about S to prove that it is a subring using the ring axioms. Well, let's see. We would have to prove that it's closed under addition and multiplication. Can't get around that. We would have to prove that the addition and multiplication are associative. We would have to prove that addition is commutative. We'd have to prove that S has an additive identity, that every element in S also has an additive inverse that's also in S. It would have to satisfy the distributive property, and those are the 6 things that we would, in principle, have to prove. However, you might have noticed that some of the properties are italicized. I didn't do that just to be fancy. All the italicized properties are going to be true regardless of what the subset S is. Right? So what does that mean? Well, let's think about addition and multiplication are associative. Whatever the subset S is going to be, addition and multiplication are going to be associative on that subset S. Addition is going to be commutative no matter what the subset S is. The distributive property is going to hold regardless of what the set S is. Those are properties that are inherent in the addition and multiplication in the ring R. And since S is using that same addition and multiplication, those properties are going to hold into the set S as well. So what that means is that all of those italicized properties are properties that are true of all elements of R, which means they're going to be true of all elements of S as well. So what ring properties are left to prove? Well, here comes our theorem. It's going to bring us our first subring test. So suppose R is a ring and let S be a subset of R. Then S is going to be a subring of R precisely when the following are true. First of all, S is closed under addition. S is closed under multiplication. The zero element of R is in S. And finally, if S is in S, then negative S is also in S. It's closed under additive inverses. Excuse me. So all of the four parts are pretty obvious. We just took the non-italicized properties of being a ring, except there is one very subtle issue, and it's actually the third one. So we know that we have to prove that S has an additive identity. The question is, does that additive identity have to be 0R? In other words, is it possible for S to have an additive identity that is not 0R? Does it have to be 0R that's in S, or some other element that's playing the role of additive identity? Well, let's prove that it actually has to be 0R. So suppose that S has some additive identity 0S, and we're going to prove that 0S is equal to 0R. Once we do that, the whole theorem sort of falls into place. All right, so in order to do that, we're going to do some computations that should be a little bit familiar from some other computations that we did when we started looking at rings. We're going to compute 0S plus 0S, and we're going to compute 0R plus 0S as well. Now, if we take 0S plus 0S, since 0S is the additive identity in S, then when we add those together, we get 0S. And note that that addition is the same addition in R, since S has the exact same addition as R does. Also, 0R plus 0S, well, that's also equal to 0S, because 0R is the additive identity in R. That means it acts as an additive identity for all elements of R, including whatever that 0S is. Well, since 0S plus 0S and 0R plus 0S are both equal to 0S, that means they're equal to each other. And if we use additive cancellation, or if you prefer adding negative 0S to both sides of that equation, we get 0S equals 0R, and that gives us our result. Okay, so let's see if we can actually apply this to a subset of a ring that we know. So we're going to define S to be the all integers k, such that k is equal to 4m, where m is an integer. In other words, S is the set of all multiples of 4. So we're going to prove that S is a ring by proving that it is a subring of another ring. Now, every element of S is also an integer, so that means S is a subset of the integers. So we're going to prove that S is a subring of Z, and that would prove that S is a ring. All right, so we only need to prove the four things, right? We need to prove it's closed under addition. Well, what does that mean? So if we have two elements in S, A and B, we want to show that when we add them together, we also get an element of S. Now remember, being an element of S means that it's a multiple of 4, so that means that A is a multiple of 4, 4 times M, B is a multiple of 4, 4 times N. M and N could be the same, could be different, so we got to use different variables, where M and N are both integers. If we add them together, this is what we get. We can factor out that 4. Notice that M and N are integers. That means M plus N is also an integer, which means that A plus B is a multiple of N, 4 times M plus N, which means that it's an S. Closure under multiplication, very similar. You can try it yourself if you like. Now for the additive identity, we have to somehow prove that 0 is a multiple of 4, but it is 4 times 0. 0 is an integer, 4 times 0 is an S, so 0 is an S as well. That's not so bad. And for additive inverse, we're going to assume that A is an element of S. We're going to show that negative A is also an element of S. We know that A is an S, so it's a multiple of 4, 4 times M, where M is an integer. And if we want to find negative A, it takes a little bit of work to prove it, but it's not too hard to prove that negative A is equal to 4 times negative M. Negative M is also an integer, so that means negative A is a multiple of 4, and therefore an element of S. And that's all the four things. So we just proved that S is indeed a ring. All right, so now let's see if you can try out some of these techniques for the subring test on the PDF file that's included with this video.